Hello everyone, Mr. Fawcett here, and we are back with another Algebra 1 lesson. Today we're going to continue to talk about systems of equations, but we're going to look at what special cases of these systems of equations look like. So before we jump into this lesson, I actually want to do a quick little review. So let me just pull up a white piece of paper here. A quick review of what special cases of single equations look like. Right, so we'll have three examples. So I might have something like 2x equals 10. Might have something like 3x minus 1 equals 3x plus 2. And for our third, we will do 2x plus 1 equals 2x plus 1. So take 30 seconds, well, maybe take you a little bit longer, to solve all three of these equations and think about what the solutions are. Okay, so if I solve the first one, obviously just dividing both sides by 2, and I'll get x is equal to 5. It's pretty straightforward. Our solution is x is equals 5. If I look at my second one, I will subtract 3x from both sides. And I will get -1 is equal to +2. So think about what the solution to this equation would be, right? -1 is never equal to +2, and there's no value of x that would make that true. So this equation actually has no solution. Right? When you get a number that's different on both sides, and the x's or the variable are eliminated, you have no solution. And let's look at this third one. Let's subtract 2x from both sides. And I get 1 is equal to 1. Well, this is always a true statement, right? 1 is always equal to 1. And in this case, it wouldn't matter what x is. I would still get 1 is equal to 1. So this equation has all real numbers as solutions. Sometimes you might see it written as infinite solutions. But the best answer is just all real numbers. So there were three different possible outcomes when we solved single equations. Right? We could get one solution, just x is equal to 5 or y is equal to 10, etc. We could have no solutions, and we could have all real numbers as solutions, or infinitely many solutions. The same idea is going to hold when we do systems of equations. We can still come up with these three options. Now, up until now, we've only done a single solution, right? One value for x, one value for y. But today we'll look at, the other possibilities as well. So let's first start with graphing, right? Because that's the first of our ways of solving systems of equations. So this says, if we have two lines on a graph, how many times can they intersect? Sketch some examples below. Can they intersect 0 times, 1 time, or maybe more than once? Well, hopefully you've had some time to sketch out some lines, but you could certainly have them intersect 1 time. Let's do red and green. Right, so maybe they intersect 1 time right here. Maybe they intersect 0 times. Whoops. So maybe we have two lines that look like this, and they actually never intersect at all. Or, and I'm going to have to erase these to give you the third example, maybe our lines are the same line. In that case, they would be right on top of each other. So those are the three examples. If you have two lines, they could be the same line, they could be right on top of each other, they could intersect once, or they could not intersect at all. And each of these have a relationship with how many solutions there are. So if we go down here, a system of linear equations may have one solution if their graphs intersect once, right? Just like these graphs do. So they intersect one time, the system has one solution, and it's where they intersect. A system may have infinitely many solutions, or all real numbers as solutions, if the graphs are the same line. And this is what we're looking at in our middle example, right? It's hard to tell, but those lines are right on top of each other. So if the lines are right on top of each other, there are infinitely many solutions because the lines intersect at every single point on the line, right? You could choose any point on these lines, and it's going to be a solution to both equations. The final possibility is that the lines have no solutions, and that's if they are parallel, if they never intersect, right? We've already talked about what parallel lines look like, right? Same slope, different y-intercepts. That will ensure that the lines never intersect, and it will also ensure that there's no point that works for both of the lines. So there would be no solutions to that system of equations. So let's put that on paper, even though we just talked about it. Linear equations will have no solutions if they have the same slope and different y-intercepts. Again, that makes the lines parallel. Question is, why would they need to have different y-intercepts? Well, otherwise they'd be the same line, right? And then they would no longer be parallel, they would be the same line. They would actually have infinitely many solutions, which comes to number 2. Linear equations will have infinite solutions if they have the same slope and the same y-intercept. So if two lines have the same slope, they're either going to have no solutions or they're going to have infinitely many solutions. So we're going to take a couple of examples down below and just look at what that would, or look at what would happen and what types of solutions we would have when we graph these lines. So take a couple minutes, graph both of those equations on the plane below, and then think about which of the categories it falls into from up above. Does it only have one solution, infinite solutions, or 0 solutions? All right, I will do the top one in red. Y-intercept is -3, slope is 5/4, so I'm traveling up 5 to the right 4. And our line is going to look like this. The second one in blue. Whoops. What's going on? There we go. Y-intercept is +4. Slope is the same, 5/4. Now, a little bit of a tangent, but if our slope is 5/4 for blue, that's also the same thing as -5/-4, right? Because if I divide two negatives together, it'll become a positive. So if I don't have room on my graph to travel up 5 and to the right 4, I could go down 5 and to the left 4, and it would be the same. So down 5 to the left 4. I'm going to get the same line as if I went up 5 and to the right 4. And you'll notice that these lines are parallel, so they're never going to intersect, which means they have no solutions. And that would be our answer. No solutions. They never intersect. And we wouldn't actually have to graph these out, right? Because if we understood what parallel lines looked like algebraically, well, they have the same slope and different y-intercepts. So if we could just identify same slope, 5/4, different y-intercepts, we know what they would look like on a graph without actually having to graph them. Graphing just gives us a visual, but again, we can understand this algebraically and know what our answer is going to be without graphing them. Let's do one more graph example. Let's do this one right here. Again, take a couple minutes, graph those, and think about what the solutions would look like. Okay, first one's a little different than normal. That is a vertical line, right? It's just x is equal to 2. So it goes through 2 on the x-axis. And we have a, oops, that's not very good. We have a vertical line that looks like that. The second one, we'll do that one in red. Oops. Y-intercept is -2. Slope is -1. So I'm traveling down 1 and to the right 1. My new line looks like this, or my second line looks like this. And we can pretty clearly see that our intersection point is right here at 2, -4. So this system of equations has one solution. This is like one we did a couple days ago or a couple of lessons ago. One solution at 2, -4, because that's the only point that works for both of those equations up above. All right, let's do a little bit of practice with substitution and elimination. We kind of know what graphs look like when we have one solution, infinite solutions, or no solutions, but now let's look at the algebraic forms. And this will be kind of what we talked about at the very beginning with single equations. So when we're doing substitution or elimination, if we get an equation that is in, if we get an equation that is false during the process of substitution or elimination, then the system will have no solutions. So if at any point you get something that looks like 0 equals 3, or 5x plus 3 equals 5x, or 7 equals 6, right? Those are all false equations. It means the entire system will have no solutions. On the contrary, if we get an identity, that's not how you spell identity. Identity. Then our system will have infinite solutions. So something like 0 equals 0, x equals x, or 7 equals 7. So let's look at a couple of examples and see, if they fall into one of these categories or not. Let's do the one on the left. Now again, it's your choice. You can solve this using elimination, or you can solve it using substitution. So think about what method would be easier, and then think about why it would be easier. So why is one method more efficient than another method in this case, for the one on the left? Well, substitution would actually be easier here, right? And it's because we already have one equation solved for one of the variables. So we can very easily substitute this in to the y in our second equation. So we're going to get 8x minus 4. Instead of y, I'm going to have 2x minus 7. And now I just have a single variable equation to solve. So let me do my distributing first. I'm going to get negative 8x plus 28 is equal to 16. Combine my like terms. Positive 8x and negative 8x, that gives me 0x. So I'm left with 28 is equal to 16. Well, right, this is false. There is no way that 28 will ever be equal to 16. So we can stop and automatically say no solutions or no solution. And that's because we got an equation that was false, right? There's no x's left to solve for. We're left with 28 is equal to 16, which we know isn't true, so we can stop and say no solutions. Let's take a look at the one on the right. So again, think about what would be easier, whether it be substitution or elimination, and then actually go ahead and work through this yourself, and then come back and check the solution on the video. So do the whole process on your own, and then come back and check. Okay, so for the same reasons on the left, we are going to use substitution here. That's the most efficient method because one of the equations is already solved for one of the variables, in this case y. So instead of 4y in my second equation, I'll have 4 times the quantity negative x minus 7 plus 4x is equal to negative 28. I will distribute. So I'll get negative 4x minus 28 plus 4x is equal to negative 28. When I combine my like terms, those will simplify, right, to 0. Negative 4x plus 4x gives me 0x, so I'm left with negative 28 equals negative 28. Well, this is an identity. This is an identity, which means it is always true. So I can stop right here, and I can just say there are infinite solutions to this system of equations. There are infinite solutions. Let's do one more. Let me pick another one. Okay, looks like we are going to do, let's do the one on the left. So, same as up above, think about what the best method would be. Would it be substitution or elimination? Think about y, and then go ahead and solve it using whatever method you choose. And see if we get 0, infinite, or 1 solution. All right, so here, it's actually not going to be easier to use substitution, right? Because none of the equations are solved for any of the variables. So we'd have to do a bunch of rearranging, right? Then we may get some fractions before we substitute, etc. So we're going to see if elimination will work. Well, right off the bat, none of these coefficients are the same, right? 20 and 10 are not the same, 12 and 6 are not the same, but they do look like multiples of one another. Right, so if I multiply this bottom equation by 2, right, if I multiply negative 10 by 2, that's going to be negative 20, which is good because that would be an opposite of 20. Right, we're trying to make those coefficients the same or opposites of one another, because then it'll be easy to eliminate one of them. So, let me bring down my first equation. So 20x plus 12y equals 20. And then let me multiply the second equation by 2. So 2 times negative 10x is negative 20x. 2 times negative 6y is negative 12y. And 2 times negative 10 is negative 20. And then we will need to add these two equations together. If I add these together, 20 minus 20x, 0x, 12y minus 12y, 0y. 20 minus 20 is 0. So I actually end up getting 0 is equal to 0, which is an identity, which means we have infinite solutions. So again, a lot of the ones you're doing in today's lesson, they're going to be one of the special cases, right? They're either going to be 0 solutions or infinite solutions. These are just two other options, right? We're still going to see systems of equations that just have one solution, right? You're going to solve them like we've been doing the last few lessons. You'll get one value for x, one value for y. today we're just showing you two other possibilities, right? Not every system will have a single equation. Some will have none, and some will have infinite. I think that's where we're going to leave it for today. I think you have enough tools to finish the rest of the problems in this lesson. As always, enjoy the rest of your day, and we will look forward to seeing you next time.